Hi boys and girls, this is the beginning of the Unit 2 lectures. We'll be discussing limits and their properties, and toward the end of the unit we will also begin our discussion of differentiation. This is lecture 2.1 entitled A Preview of Calculus. So what is calculus? Calculus is the mathematics of change, changing quantities, quantities that are changing with respect to time or with respect to other quantities. There is a fundamental difference between pre-calculus mathematics and calculus. Pre-calculus mathematics deals with static quantities, whereas calculus deals with dynamic quantities. I should clarify that when I mention pre-calculus mathematics, I'm not just referring to the course that's named pre-calculus. Pre-calculus mathematics refers to any mathematics prior to calculus. Calculus is the mathematics of change, which means this year we'll be learning processes which allow us to model the changing quantities of this world with accuracy and precision. Calculus is used in every branch of the physical sciences. It's used in computer science, statistics, engineering, economics, business, medicine, in any field where a problem can be mathematically modeled and an optimal solution is desired. With calculus, you're able to determine a non-constant rate, and in addition, you can accumulate the amount of change based on that non-constant rate in order to get a total amount of change in that particular rate. It's a pretty big deal, I'm not going to lie. The development of calculus and its applications to physics and engineering is the most significant factor in the development of modern science. The Industrial Revolution and everything that has followed from it, including all the major advances of the last few centuries, would not have been possible without calculus. Now let's discuss a couple of scenarios that highlight this difference between pre-calculus and calculus mathematics. With pre-calculus, we're able to find the slope of a line. If we know the coordinates of any 2 points on the line, we're able to calculate the change in vertical distance over the change in horizontal distance in order to get the slope of the line. With calculus, we're able to find the slope of a curve. More accurately, we're finding the slope of a line tangent to a single point on the curve. With our knowledge of this point and a knowledge of the function, we'll be able to use calculus to get the slope of that tangent line. Furthermore, we can use that same function to get the slope of the line tangent to this curve at another point. You can see that as I choose different points on the line, that the tangent lines I draw have different slopes. Well, the function that I find will be able to tell me the slope of the tangent line at any point on this curve. Back to pre-calculus, we're able to find the area of a known geometric figure, like a rectangle, a triangle, a circle, etc. But with calculus, we're able to find amorphous areas with non-regular boundaries, area under a curve. And notice in this particular case, even though this is a line, this is a line, this is a line, this isn't a line. So this doesn't fall into the category of any of our known geometric shapes. And so without calculus, we at best would be only able to find an approximation of the area under this curve. Exactly what is it that takes us from the mundane world of pre-calculus mathematics to the amazing world of calculus? Well, I'm glad you asked, boys and girls. The connection between pre-calculus mathematics and calculus requires the reformulation of pre-calculus mathematics through the use of a limit process. This is very important in calculus. Without it, we would not be able to do the things that we need to do. Therefore, we take our pre-calculus mathematics through the limit process, and in doing so we get calculus. The notion of a limit is fundamental in the study of calculus. To understand how the limiting process works, we'll examine two classic problems in calculus, the tangent line problem and the area problem. Of course, these are the problems that we looked at briefly on the previous slide, but we're going to look at them in a bit more detail now. First, we'll look at the tangent line problem. Finding the tangent line at a point P on the curve is equivalent to finding the slope of the tangent line at a point P. This is what I mentioned before. We don't actually find the slope of a curve, but that's sort of shorthand for explaining that we're finding the slope of the line tangent to that point on the curve. Now, we are tasked with finding the slope of this line. All we know is the coordinates of this point, and we know what this function is. Now, prior to calculus, that would not be enough information. And if you had to find the slope of this tangent line, you might think, well, I could probably get a pretty good approximation if I choose another point on the function that's pretty close to P, and with those two sets of coordinates, I could find the slope. So we would start with maybe P and Q. Let me grab this line and see what that would look like. Notice this is a secant line now, not a tangent line. And you can see that with these two sets of coordinates, we could find the slope. It would be an approximation of the slope of the tangent line, but it's not a great approximation. So you might think, I could probably do better if I move closer to point P on the function. And of course, that's true. The slope can be approximated using a second point on the curve. Furthermore, you'll get better approximations by using points that are closer and closer to your target point. So now with the red line, we have this point and of course P. We would be able to calculate the slope of that line, and it would be an approximation of the tangent, but it's not really a great approximation. We could continue this process with a third line, using a point that is closer to P than the previous two were. You can see that now, using that point and P, we could calculate the slope of this secant line, and it is closer to the slope of the tangent line. But it's really not that great of an approximation. We can see that there's a distinct difference between the slope of this line and the secant line that we have created. Well, what we're going to do with the limit process is we're going to continue getting points closer and closer and closer and closer to P. What if the coordinates of P were something like, let's say, 3, 2? And we decided to choose a point so close to P on the curve. Maybe the coordinates of that point that we choose would be something like 3.0001 and 2.0001. You can see that if I used these 2 points and calculated the slope there, I would definitely get a slope that is very close, a really good approximation of the slope of the tangent line. But it would still be an approximation, not exact. So the idea is, again, with the limiting process, what if we could get a point so close to P that it's only a virtual distance away, not an actual distance away, but we create a virtual construct, a point that's kind of not real, but a pretend point, and using that point that's not really much distance away at all, perhaps no distance away, and point P, we create a slope formula, and we're able to calculate the slope of that line. The limiting process allows us to do this. Now let's look at the area problem. What if we were asked to find the area under this curve? Now again, since it's not a regular geometric shape, we don't really have a formula for calculating this area. We might get creative and say, well, I can approximate the area. I could use a known geometric shape like a rectangle, and I could draw some rectangles and try to approximate, or maybe get a good approximation of the area under the curve. So in this first little graphic, you see that we have divided the x-axis into 4 regions. These are 4 rectangles, and these increments on the x-axis are the width of each rectangle they're forming, and then a function value at various points on the x-axis represent the height of each of the rectangles. I could calculate the areas of these rectangles, add them up, and have an approximation of this area under the curve, between the curve and the x-axis. So this region here, and this region over here. Well, it is an approximation, but we can clearly see it's not a very good approximation. Now, if you were using this method, you might think, wait, if I use more rectangles, I'll get a better approximation. And that's what we see here, 8 rectangles. Now notice that the increments on the x-axis are smaller. Once again, these increments represent the width of each rectangle, and then function values on the curve represent the height. And so once again, once you've drawn these little rectangles, you can calculate these areas, add them up, and get an approximation. But again, you see that it's not that great of an approximation. And you think, I will make more rectangles. Here are 16. And the increments on the x-axis are smaller, which means more function values, more heights, more rectangles. When you add up those areas, you get a better approximation. Here are 32 rectangles. If only we could keep adding rectangles. If only we could get an infinite number of rectangles. As you increase the number of rectangles, the approximation becomes closer to the actual area of the region. And when you increase the number of rectangles to infinity, you get the actual area of the region. How do we do that? How do we increase the number of rectangles to infinity? Through the limiting process. The idea here is that now these widths on the x-axis would be virtual widths. And so if we had an infinite number of rectangles that are constructed by using every number on the number line, all of the real numbers, and there are an infinite number, and every corresponding function value, which means there would be an infinite number of heights, these rectangles of virtual width, adding all of those areas up would actually be the exact sum of the area under the curve. That's what the limiting process allows us to do. Your goal is to determine the limit of the sum of the areas of the rectangles as the number of rectangles increases without bound. That, of course, means as we let there be an infinite number of rectangles. That ends today's lecture, boys and girls. We've had a sneak preview into the mystery of calculus. I leave you with a stanza from a poem by William Blake. To see the world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. Calculus will allow us to hold infinity in the palms of our hands. God bless you, boys and girls.